Let's have a look at some of the key ideas in the bivariate topic at level 3. So the first thing we need to do is think about our variables. And we've got two types of variables. We've got a response variable, which is sometimes called our dependent variable, and we've got our explanatory variable, which is our independent variable. Now we will plot the explanatory variable on our x-axis and our response variable on the y-axis. Now the hardest part is figuring out which variable goes where. So one of the things that you want to think about is, if I know this information, can I use that to predict the other information? So you've got to think about the order in which it happens. So for example, if I know somebody's age, I could predict their height. Okay, so what happens first? We get older first, and as we get older, our height grows. So these are the kinds of things we want to think about. What's the order in which things happen? So here's an example. On one axis we've got the number of cars, and the other one we've got the revenue. So this is talking about a car wash. So the more cars that we have, the more income we're going to get in. But the way order in which it happens, the car arrives first and then they pay. Okay, so we've got to make sure that this variable here, the number of cars, that is going to explain what the variation that we see in our response variable. So the other thing with correlation, with bivariate, is this idea of correlation versus causation. So this is just a little flow chart to give you an idea that these two ideas are different. You cannot interrelate these. I can talk about correlation and association, okay, but I can't mix this up with causation. So for example, I might draw a graph of self-esteem versus depression. Okay, so if I draw a graph of self-esteem versus depression, and I might find that people with low self-esteem have, in fact it won't be that, people with low self-esteem could have higher rates of depression, and people with higher self-esteem have lower rates. So I might find there's some kind of relationship with them. But this is not a causation, this is just a correlation. Because is it that the low self-esteem causes depression? Is it that having depression causes somebody to have low self-esteem? Or is it that there's something else going on, that some other event or genetics has occurred that causes somebody to have both low self-esteem and depression? Okay, so when we're just looking at a graph of self-esteem versus depression, that isn't a causation graph. That is just looking at for some kind of relationship, some correlation or association. So be very, very careful. The only time we can talk about causation is if we have done a formal statistical experiment. Okay, that's the only time we can talk about causation. So once we've got our data, there's a few patterns that we want to identify. We want to start by looking for what kind of trend we have. Now, one of the things I'm going to recommend that you do is you kind of join the dots, hit all the lines at the top, hit all the dots at the bottom, and that gives you an idea of the pattern. It helps your eyes see much more clearly what the pattern is. So in this case, I've got a linear pattern, and I want you to think about that like as a paintbrush. So if I'm just colouring this all in, my paintbrush is just going in that general direction. Now, how do I know it's difference between a linear or non-linear? Think about going up a set of stairs, all right? As I walk up a set of stairs, each tread is the same width and height. And so that means my gradient is constant, okay? And so that's one of the key ideas behind a linear graph, is that we've got a constant gradient. The gradient's changing by a constant value. In terms of nonlinear, if I hit kind of the edges and I hit the bottom edges, we can see that there's some kind of curve pattern going on there. And I can see that at the bottom here, my gradient is not very big. As I go up further, the gradient is getting steeper. All right, so in this one, we've got a changing gradient. And that is one of the hallmarks, one of your key ideas behind identifying if it's linear or non-linear. Equally, this one here, again, hit all the values at the top and hit all the values at the bottom. Still a curve going on. The gradient here changes from being positive through to 0 to being negative. So again, its gradient is changing. The only other type that we could have is if we have no trend whatsoever. So when you've got data that's just randomly scattered across all of the graph, there's no patterns that you can identify. And in that case, we would say there is no trend. Okay, association. That's thinking about what direction it is going in. So I'm thinking about if I was to put a kind of a line through that data, is that line going up or is that line going down? So is it positive or is it negative? Now in terms of justifying that, we always want to think about what is happening as our x variable is increasing. All right, so it's always thinking about as x increases. And if it's positive association, as the x increases, my y variable is increasing. Okay, whereas for a negative association, if I'm going from, say, this data value to this data value, as my x increases, the y variable is decreasing. Okay, so that's kind of the justification we always want to talk about. As x increases, is the y variable increasing or decreasing? So is it positive or a negative relationship? Okay, the third component is about the strength of the relationship. So one thing we said was if the data is just randomly scattered throughout the whole entire graph, there's no patterns there, that tells us we have got no relationship. Whereas if I've got all the data values almost in a lovely straight line, then that tells me I've got a very strong relationship. Okay, as that relationship gets a bit more scatter, so we can see if I draw these lines above and below, the moderate relationship is wider. It's wider now than that strong relationship was. And if I think about a weak relationship, that is it's wider again than a moderate relationship. Okay, so it can be positive or negative, but the strength could be very strong, moderate, weak, or no relationship whatsoever. And this is the same kind of thing, just with a negative relationship. So I can have a nice, tightly packed data set for strong, a little bit wider for moderate, and wider still for a weak relationship. Now in terms of evidence for the strength of it, now that we don't have to do this, but sometimes this comes up. It's not technically in the curriculum, but it's a way for us to be able to look at this strength in a calculated way. And so we use something called the correlation coefficient. We can only use as a backup because what you see is the most important part. So I've got down the bottom, I've got the scale, the R value, that correlation value, can go anywhere from -1 to +1. Now, if it has a value of 0, that means it's got no relationship. So in terms of my graph, it's just a whole bunch of data just randomly scattered around with no particular pattern. A correlation of 1 tells me I've got a very strong positive relationship. Correlation of -1 tells me I've got a very strong negative relationship. And as we get closer and closer to 0 from either end, so as we're going down from +1 or going up from -1, the strength of the relationship is decreasing. So here's some little graphs to show you a bit more. So we've got our R value of 1 would give us a perfect straight line relationship. Then if I had an R value of 0.8, that gives us a reasonable, that would be moderately strong. By the time I'm getting down to 0.3, that relationship is a lot wider. Okay, the strength is a lot lower now. And so that's something that we can use to supplement our evidence if we have this information. Now, so there's a couple of key ideas about this. That correlation only works if the relationship is linear. So if you've got like a curved relationship, so show below, here I've got a perfect quadratic equation. Okay, that's a lovely quadratic relationship. But when I calculate the correlation coefficient for this, that's going to give me an R value of 0, which would mean no relationship. And it doesn't mean no relationship, it means no linear relationship. Okay, so we have to be quite careful that we can only use this if we have linear relationships. Okay, variation and scatter. So when I kind of draw my lines above, draw my lines below, what I'm looking for is how wide is it across for different values of x, what's happening to the width of this. And you can see with the first one that it's pretty constant. So this is what we call constant variation or constant scatter. Okay, for different values of x, for different x values, the scatter is about the same. Whereas the second graph here, if I draw my lines above and below, okay, what you can see is as the x values are increasing, okay, as x increases, the variation, in this particular case, the variation is increasing. How wide these lines are, how far apart they are, that is increasing. So this is what I would call we would call a fan effect. Okay, it's like a fan. When you open it up, as the x increases, the fan gets wider. If it was the other way around, so you had data that followed this kind of shape, then you can see that this here, that's what we would call a funnel effect. Okay, that as x increases, the variation is decreasing. So that's another pattern, the last pattern that we can look for in this type of data. Now, if we want to fit a line of best fit, that's thinking about, right, where would I put the line? Is that a good place to put it? Is that a good place to put it? Is this a good place to put it? How do we decide what the best place to put the data is? And there's something called least squares regression, and what that does is it comes up with a best estimate based on trying to fit a line that goes through the middle, and when it adds up all the distances above that the data is above the line and all the distances that the data is below the line, that those values should balance out. All right, so we want to have a roughly number of equal values above and below the line so that the distances between it are as close as we can get. So when we fit a line, well, we know our general equation of a straight line, y equals mx plus c, and so we can use that information then to make predictions. And that's what we're going to do. So in order to make predictions, if we've got a linear one, we would find that line of best fit through the middle, use that equation to come up with the prediction model. However, what if I've got a graph that really looks like that? In actual fact, that looks far more like either an exponential model, or I might possibly be able to fit that into some kind of parabola or quadratic, etc. And so there's some other curved models there that would fit much better. For the third graph, again, if I draw a line kind of going through the middle, that's about what I would see. And I'm wondering, maybe that is a negative quadratic. Okay, this is where our knowledge of all these different functions becomes quite useful. And so we need to be able to look at the data and see which model do we think is the most appropriate. Is it a straight line? Is it a quadratic? Is it a cubic or an exponential or a logarithmic or sine or cos or any of those other ones? Okay, so this is where we need to eyeball the data and see what the pattern is. So if I looked at these two graphs here and I wanted to think about which of these two graphs would give me a more precise estimate. So if I think about what does that word precision mean? The more precise something is, the more confident I am. And if I've got data that is all scattered quite closely together, then that means I'm going to be much more precise as opposed to data that's more spread out around the line of best fit. There is a lot more variation in that data. So that's going to give me a more variable result, whereas I would rather have a much more narrow scatter. So in order to do the prediction, often you'll be given an equation. So in this case, we've been given this equation here. Fuel efficiency in the city is equal to negative 0.017709 times the weight plus 47.048. So I can look at the data here and say, right, well, if I was to choose a car that weighed 1,200 kilograms, I could substitute that value. So I could substitute a weight of 1,200 kilograms into the equation above and find the fuel efficiency of negative 0.017709 times 1,200 plus 47.048. And that would give me a fuel efficiency of 25.8 kilometres per litre. So I'm predicting that for a car that weighs 1,200 kilograms, that they would be able to travel about 25.8 kilometres for every litre of petrol. So if I am predicting within the range of the data, and here my data starts from just over 800 kilograms to say 1,900 kilograms, if I'm predicting inside that range, I can see there, I'll have a reasonable amount of confidence in that prediction. But if I wanted you to predict a car that weighed 2,500 kilograms, we have absolutely no data there. So that using this equation, while it's a lovely equation, I have no idea about whether this equation will hold going beyond that part. Because it might be that actually the graph is going to do something like this, or maybe it's going to do something like this. I just do not know, and so I don't want to extrapolate beyond the data. Okay? I just want to be able to make predictions within the data because I actually have some information about what is happening with the model inside that range. Now I can extend these prediction values, and so when I predicted before, I said for a car that weighed 1,200 kilograms, and we substituted into the equation and found the corresponding value of 25 point something kilometres per litre. Now that is giving me a specific range, a specific value. But what I know is when I look at the data at that point, okay, so when I look at the data around about 1,200 kilos, sorry, let me just draw a straighter line. So if I'm looking at that point there, we can see that the data itself is, when I kind of draw my lines above and below, I can see that there is a range of values that the data could take in that area. Okay, and that's the prediction interval that I want to be able to come up with. So I would say that yes, my best estimate is that a car that weighs 1,200 kilograms would have a fuel efficiency of 25.8 kilometres per litre. But in actual fact, given the amount of data that I have and the variation in the data, it could be anywhere from 22 kilos all the way up to around about 30 kilos. All right, so that would be my prediction interval, being able to say it could be anywhere from 22 up to 30 kilometres per litre, given the amount of variation there is in the data at that point. All right. Okay, outliers. There are a number of different types of outliers. Remember, we're looking for patterns. So when I'm drawing my graph, there's the main pattern. This value over here is an outlier. It's unusual. It's not following the pattern. So this is an outlier because it has a large x value. All right. In terms of its y value, if you think about its y values, well, that's not unusual at all. But in terms of the x value, the previous x value stops there. This is a long way away from it. That's what makes it into an outlier. We could have ones, again, here's my pattern. If I could have a value up there, which is an extreme y value. So my last known y value stops here, and this is quite a way beyond that point. There's quite a big gap between the previous values and this point. We could have a value like this one here, which is extreme in both its x and y value. So in terms of its x value, that's quite a distance that way, and in terms of its y value, it's quite a distance that way. So that would be extreme in both x and y. Or we could have a point where here's my trend. This value here, it's not a long way up on the x or y axis in any direction, and in fact it's quite common in both x and y values. However, it does not fit the pattern that we see in the rest of the data. Alright, so that point does not follow the general pattern. So that's what we're looking for as an outlier. It's values that are unusual. They're not following the pattern that we see. So some outliers are also influential points. And an influential point means that it's a point that has a lot of influence over our model. And so what I've got here is if I've got this particular outlier down the bottom, if I do a line of best fit, I can find that that would give me a correlation coefficient of 0.4. If I do this again, fit the line of best fit to it, after I've removed that point, my correlation coefficient changes to 0.7. So that's saying this one data value has changed my correlation coefficient from 0.4 to 0.7. Equally, I would look at what the gradient of that line is and the gradient of this line, and how much has that gradient changed. And the bigger the changes, the more influential the point is. Okay, another type of analysis that we can do is looking at subgroups. So when we just look at this first graph on the left hand side there, we can see that there's, yes, I can draw my lines above and below, and I can see, look, there's a positive, probably linear trend, quite weak relationship going on between these two variables. If I colour this in by subgroups, you'll actually see, and that's what the graph on the right hand side here is now looking at, we will see there's actually two clusters going on. We've got a cluster of one group here and a cluster of another group there. And it could be that this cluster here is the females and this cluster here is the males. Or it could be that one group is a particular ethnicity and a different ethnicity. It could be the area in which they're located. There's so many things it could be. And that's when being able to colour in by subgroups is really useful. We're looking for patterns. And there's most of our key ideas.